Okay, so let's continue. So for for the mapping function for the logistic regression should be looks like this with the nonlinear function g, and finally it can be represented like this. So what does that mean? What does that mean? The shape of the g function, it looks like g over z. It looks like this. So what does that mean? So fw of x is larger than 0.5, then we can determine y is equal to 1 as a positive class. So when is that statement satisfied? W transpose x is larger than 0. So because this is the z, right? So it means that z is larger than 0. We can determine the y is equal to 1. The W transpose x is less than 0. So we can say that y is equal to 0. So this is the definition of the logistic function. Then what is the decision boundary? What is the decision boundary? Okay, let's say we have a sample x1 and x2. Sample, how can I represent? Yeah, represent the x1, x2 like this. Okay, if we use the similar notation with the linear regression, we can represent x1, x2 like this. Anyway, so this will be the x2 over x1, x1 over x2. Okay, so we have the mapping function like this with the nonlinear function with some kinds of linear regression, linear combination of the coefficient and the input feature x, something like this. So what is the decision boundary of the classification problem? Okay, let's say there are samples like this and like this. Okay, so they have some kind of feature x1 and x2 with the class label 2 kinds of class label. In this case, there are class label. Let's say this is class label 1 and this is class label 2. Okay, then we want to find the classifier that separate these two sample training sample. Then what will be the line that separate these two sample? For example, let's say W0 is equal to 3, W1 is equal to 1, W2 is equal to 1, right? No, W0 is -1 and -3, something like this. Then from this slide, if this linear dot product is larger than 0, we can say that this is a positive sample like this. So in this case, if this value W transpose x is larger than 0, we can say that this is the class 1, and if this value is less than 0, we can determine y is equal to 0. And this means -3 plus x1 through the x2 is equal to 0, and x1 plus x2 equal to 3. So this equation represents like this straight line, right? So it means that this straight line, across this straight line, this part will be the y is equal to 1, this part will be the y is equal to 0. So yeah, in this case, this straight line is called, decision boundary. Decision boundary. So what does that mean? The decision boundary means this straight line, if we find this straight line, and if we have the new input solution like this, we can determine this is the class 1 or class 0. So this is the decision boundary for classification problem. Actually, this decision boundary can be also nonlinear shape. Actually, we just consider here as a straight line, but if we formulate the, where's that? Like this one with the additional square term, okay? Some of you are confusing of this. Okay, let's say this is the first element of feature, and this is the second element of feature. This is first element of square, and second element of square. Yeah, let's say looks like this. It'll be much better. Okay. And if we found the value W0 is equal to -1, W1 is equal to 0, W2 is equal to 0, W3 is equal to 1, W4 is equal to 1, then we can represent this part. This part is like this, okay? So what does that mean? X1 square plus X2 square is equal to 0, like the circle shape here. Okay, so if the value is the outside of this circle, we can determine y is equal to 1, and if some kind of the feature inside of this circle, we can say that this is the class 0. So in this case, this circle will be the decision boundary. So comparing to this example, this decision boundary can be the nonlinear shape. Okay, so we can determine any kind of the decision boundary shape by formulating this part in a various way. Okay, so yeah, it was the mapping function. Then we also need the cost function similar to the regression problem. Okay, let's say we have the training set. X was the, what was that? X was what? X was the, let's say, okay, let's say input vector. And y is the class label, like this, like this one, and like this example. Okay, we have let's say we have a training set like this with a m example, and each input vector x will be the m plus 1 by 1 vector. Okay, then we have the mapping function for the logistic regression problem or classification problem, something like this. The question is how to estimate this parameter w. This is a similar procedure to the linear regression problem, right? We have to find the parameter w, right? So first of all, let's say we have a very powerful loss function MSE. Then why not just use this MSE loss function to solve this classification problem? So yeah, let's say we have mapping function with the class label, right? Then we can just minimize this MSD loss function, right? Then we can, anyway, we can find this W, right? Then minimize this loss function. Then there's a problem, because in the logistic regression problem, we define the mapping function looks like this to satisfy this constraint, right? So actually, that function is a nonlinear function. That this function is a nonlinear function looks like okay, let's say looks like this. This is a nonlinear function, right? So because of this term, when we plot the cost function with respect to the W, the shape of this cost function looks like this. So actually, it's really hard to optimize to the global minimum, and there are several kinds of the local minimum here. So it's not a good loss function for the classification. So we need another loss function that satisfies the shape of the loss function looks like this. Looks like have the global optimum here comparing to this one. By using the gradient descent, we can easily find the solution than this previous MSC loss. Okay, so then which loss function is satisfied this condition? Yeah, here is the definition. So we need an additional loss function for the logistic regression. So we introduce the logistic regression cost function. So the cost function, as you know, the cost function is defined with the output of the mapping function and the real output and ground truth. Okay. Then there are we can use the two kinds of the equation. The first equation is that if the yn is equal to 1, we can determine this loss function, and y is equal to 0, we can use this equation. Let's see the property of this equation. Okay. First of all, how can we draw this? Let's say this is some arbitrary notation. So this function will be the y is negative log x, right? Do you know how to draw this one, right? At 1, the shape of this one looks like this, right? But with this negative term, the shape of this looks like this, okay? But we only consider this mapping function defined from 0 to 1. So the shape of this loss function looks like this from this one, right? It should be met here. Okay. So there are several properties of this loss function. So if yn is equal to 1, and the output of this feature, this mapping function is equal to 1, the cost is 0, right? What does that mean? If yn is equal to 1 and fwxn is equal to 1, it is the correct, right? In this case, the cost is 0 because there's no penalty of these samples. But if the output of the mapping function is close to 0, so the difference between the ground truth and estimate values are larger. It means that cost or the penalty of this sample should be maximized. or infinite, because it should be looks like this. So in this case, we will penalty the learning algorithm by a very large cost when the incorrect samples. So this is the first equation. The second equation of this sample, okay, let's use the blocker. Looks like this. Okay, please yourself to draw this one, because you know how to draw this one. Okay, so in this case, this has the opposite property compared to this one. So this is the logistic regression cost function. So to summarize, we can, okay, to find this parameter, we need a cost function looks like this across the n variable, n samples with a cost value. So for logistic regression, we can use this cost function, right? Then is there any simple way to represent this cost function? Yes, because there we only consider yn is equal to 0 and y1 is equal to 1. It means that this cost function can be represented by this in a single equation. These two equations are same? Yes. Why? Because if y is equal to 0, this term will be 0, and this term will be just to 1, and this term, right? No. Variable log 1, right? This is exactly same, and y is equal to 1. This term should be 0, and it should be negative log fx(xn), right? So as you can see here, we generally use this general form of the loss function for the logistic regression problem or classification problem. Okay, so here are we now. For the loss function, aggregated cost of xn and yn, we can represent our loss function for logistic regression looks like this from here. Okay, so the problem will be the what? Find the parameter w that minimize this loss function. Okay, then this is a training procedure. Training procedure for classification. Then, if we found this parameter w, now we have a mapping function like this with the estimated w, and if there is a new sample with a feature vector x, then we can determine this probability, this output of this input value. So this will be the testing procedure for classification. Okay, so to solve the logistic regression, we can also use the gradient descent algorithm similar to the regression problem. So this gradient descent algorithm can be represented looks like this. Okay, and we want to find the w, then minimize this lw. Okay, so then in the gradient descent algorithm, we use the iterative solution to remember, right? So the previous wj is updated by by summation negative learning rate alpha of gradient LW with respect to the WJ. So this will be the new WJ. So this will be the this one step is simultaneously updated for whole WJ. So this is a gradient descent for logistic regression. I just briefly skip this part because most of this part is similar to the regression problem. The main difference is just here. Okay. So okay, from this equation we can derive this one from this equation, right? Then you can do that yourself. Okay. So anyway, if we find the gradient of this equation with respect to the WJ, it looks like this. No, like this. Do you remember this shape, right? Where do you see this one? Where do you see? If you remember the gradient descent for multiple features, the shape looks like this, right? Here. Actually, there are very interesting thing. This part, the update part is exactly identical to linear regression. Right? But main difference is this part is in the logistic regression things. This part is the nonlinear function like this, but in the linear regression problem, this part is just a linear equation. So that's the difference. But each gradient term is identically same as the linear regression problem. Okay, so this is the gradient descent for the logistic regression. Okay, until now, we just think about the two-class classification problem. Then how can we extend this two-class classification problem as the multi-class classification problem? There are several kinds of the problem setting for multi-class classification, such as the email foldering or tagging, like the work, friends, family, hobby. And let's say it will be the class 0, 1, 2, 3, or medical diagram. Let's say it's just the class, something like this. And there are another example, weather classification, like sunny, cloudy, rain, snowy. Yeah, there are several kinds of the multi-class classification problem, right? Actually, the most machine learning problem can be formulated in a multi-class classification problem rather than just binary classification problem. So, as you can see here, this is just a binary classification task, and this is a multi-class classification task. So as we discussed previously, to solve the binary classification problem, we can just find this decision boundary. We can just find the decision boundary that separate the training sample like this, right? But in this case, a single decision boundary cannot separate these three kinds of the training sample, right? Then how can I find the decision boundaries that separate this multi-class? This is a one versus all technique. What does that mean? What is the one versus all technique? Let's say there are three classes, like the class 1, class 2, class 3. So this means the class 1, this means class 2, this means class 3. Okay? So what I want to do is we want to find the three kinds of decision boundary for each class. What does that mean? Okay, let's just considering this class 1. In this case, we can think another class sample is the negative and this is the positive sample. Then we can find the decision boundary looks like this, right? And another case is that if we just think these samples as a positive and the remaining samples as a negative, we can find the decision boundary like this and like this. And in this case, we train the binary classifier for class 1 and classifier for class 2 and classifier for class 3. Then now we have three kinds of classifier for each class. Then what can we do? If you remember the previous slide, this mapping function, output of this mapping function is the probability, right? Of class 1 of X. So it means that, okay, we have input variable vector X. Then we want to find the probability of this input variable X. Then we can say that, okay, this is the probability of the class I of the input X with the trained learnable parameter W. Okay. So from this one, we can determine the probability of each class. Then we can just choose the biggest probability class. Okay. This is the one versus all technique for multi-class classification problem. Okay, so yeah, let's summarize the multi-class classification problem. So first of all, training the logistic regression classifier, let's say f subscript w and superscript I of x for each class I to predict the y equals I, like this. Then this is the training, okay? Training procedure or training page. Okay. Training page and testing page. On the new input X, pick the class I that maximize like this. So if we found this logistic regression classifier for each class, then we can just pick the most high probability of the class label I. Okay, that's the multi-class classification problem. Okay, this is the last topic of today's lecture. Actually, from until now, we have learned the discriminative model. What was that? What was the discriminative model? Okay, let's say if we have the feature X, we want to find the output, right? We want to find the output class. So to solve this one, we train the decision boundary between classes. The example was the logistic regression and the SVM. Actually, we didn't learn the SVM yet, but we will learned this SVM next week. Anyway, so the discriminative model just train just to find the probability of the y of x. Okay, so decision boundary looks like this. Then okay, what is the generative model? Generative model means it tries to model the p x comma y. It means that it is what? Joint probability. What does that mean? What does the joint probability mean? This generative model is trying to model the distribution of the class. What does that mean? Okay, from this example, the generative model to model the distribution of these class samples and this class sample. Okay, with this generative model, we can classify a new sample using these two generative model. Okay, so using this generative model, using these two kinds of generative model, we can determine the probability of this new sample, whether this new sample is derived from this class or this class. So this is the generative model. Okay, so let's see the detail. So this discriminative model learned the probability y bar x given x. I mean the probability of the class y given x. So this is the discriminative model too. And in generative model, they try to train and they try to find the probability of x given y. So this is the distribution of sample x given y. As you can see here, we can model we can find some parametric model that fit this distribution of the class 1 and class 2. And then we can find this probability, and we also need the probability of the each class. So in this case, x is called the feature, y is called the label, and y is called the prior. Okay, what does that mean? Let's see the detail. Okay, let's suppose that we sorry about that. Okay, let's suppose we have modeled the probability of x given y and the probability of the y like this, and then now we have the new feature x in the testing page. We want to know the probability of the class y is equal to 1 given x. Then we can represent this, looks like this. Px given y is equal to 1 times p y is equal to 1 over px by Bayesian rule. You know what is the base rule, right? Please find what is the Bayesian rule. Okay. Anyway, so this we can represent the probability of the class y equal to 1 given x looks like this. So it means that comparing to the discriminative model, just to directly find this mapping, this probability in generative model, we can find this probability from this one and this one. Okay, so from this one, we can say that this is the posterior, and this is the likelihood, and this is the prior, and this is the evidence. Okay, we can say it looks like this. And this part, P over X, probability of the X, will be estimate as the summation of the joint probability X, Y by marginalization. To remember what is the marginalization in the first lecture of this class. Okay, then from the definition of the joint probability, it can be represented like this. Okay, summation of this term across the every class. So this is the representation of the generative model using the Bayes rule. Here's the example. Okay, in this example, this W means the class label, class 1 and class 2, and X is the feature. So what you want to do is to find the probability of the class W given X. If we use the discriminative model, we can just find this mapping function using the decision boundary or something like this. But in the generative model, first of all we have to find this joint probability. I mean the class conditional probability distribution here, right? And with the prior term here, this one can be represented like this. What does that mean? In X is equal to 14, the probability of the class W1 is equal to something like 0.5 or 0.5, something like this. So this is the generative model too. Okay, so here is another example. Okay, suppose that we've trained the generative model and get the new test sample X. So what is that meaning of the trained generative model? Is that we found this one, right? So it looks like this. Okay, then what is the probability of the class y is equal to 1 given X? How can we derive this from this equation? Okay, how can I do this? X y equal to 0, y equal to 1 time, right, from here, then probability y is equal to 1, y is equal to 1 times y is equal to 1 plus f x y equal to 0, y equal to 0. Okay, so it is what? 0.6, 0.5, 0.5, 0.5, what is that? 0.3 and 0.01. What is that? Should be removed, and 4 times 3. It will be what? Yeah. So probability of the y is equal to 1 given x should be 0.75. Okay. So this is the general idea of the generative model. Actually, for the generative model, there are so many things to learn and to do. But in this course, I want to focus on the discriminative model and going deeper. What is a discriminative model? How can we derive our model in our machine learning problem? So I just look through the what is the generative model, and in the second part of this course, in the deep learning part, I think we have a time to discuss the generative model in the deep learning world, so we can discuss further in the next setup. Okay.